Let's find a recurrence relation for this differential equation using power series. So let y equal the sum from n equals 0 to infinity of c sub n times x to the n. When you take the derivative, we're going to bring down the exponent and subtract 1. And every time we take the derivative, the index here increases up by 1. So the first derivative will be n equals 1. The second derivative is n equals 2. And then we have to bring down the power twice for the second derivative. And that's why we have n and n minus 1. So we plug this back into the original differential equation. And at this point, I distribute the sum n equals 2 to infinity to both the x squared and the negative 1. What happens is when I multiply by x squared, this becomes x to the n. And then I have minus the sum. And when I multiply this x here, it becomes x to the n. And then plus the last sum here. Okay, at this point I can change the indexes because I want them to start at n equals 0, and I want x to have a power of n for all of these. Okay, so the first one starts at n equals 2, which I could just put n equals 0 because when n equals 0, this is 0, n equals 1, this is 1. So those are going to be both 0, n equals 0 and equals 1. So I can just replace this with n equals 0. The second one, I'm going to put this n equals 2. So it's going to go down by 2, which means I have to increase this up by 2. So instead of n, it's n plus 2. Instead of n minus 1, it's n plus 1. And then n and n minus 2 also go up by 2. This sum right here, we start with n equals 1. But when n equals 0, I have 0 times the rest. So that's just 0, which means I can include it. And this one should be n equals 0. Well, oh, I see. This one, technically, you multiply the 2x, so it should be 2 times c sub n times x to the n plus 1. But problem is I want x to the n, so I have to subtract the n plus 1 and make it x to the n, which means c sub n becomes c sub n minus 1, and I raise this index to n equals 1. So that's what's happening over here. So not all of these sums start at n equals 0. It's more important to get x to the n for all of these, because then you can factor out the x to the n. So like at this step right here, I just brought it all under one sum and then factored out the x to the n. And so I just looked at this. I ignored the sum and x to the n because basically you want this coefficient to be 0. And here I took the n minus 1, c sub n, and these two, moved it to the right and multiplied both sides by negative 1. And then I factored out a c sub n from both of these. You got n squared plus n. And finally I just divided both sides by n plus 2 and n plus 1. Okay, so this is my recurrence relation. Okay, so now let's talk about the radius of convergence. So I'm going to divide both sides by x squared minus 1. And so here we see that at x equals 0, 2x over x squared minus 1 is going to be analytic, since power series at x equals 0 is of this form, which is a convergent power series. And the theorem says that the radius of convergence is at least as large as the distance to the nearest singular point. In this case, a singular point is when x squared minus 1 is 0, which means x squared is 1, or x is plus or minus 1. So the singularity is plus or minus 1, so the radius of convergence is at least 1.